All right, let's get right into it. Deep down, at the very heart of literally every piece of modern tech we use, we're talking your phone, your laptop, even the most powerful supercomputers on the planet. There's this tiny, elegant little structure. It's called the PN junction, and it is the fundamental gatekeeper that controls how electricity flows, making our entire digital world even possible.
So, the whole story here really kicks off with a question that sounds simple but is actually pretty profound. How in the world do you build a one-way street for electricity? How do you make a valve that lets current flow one way but just slams the door shut if it tries to go backwards? Well, the answer is a really beautiful piece of physics.
To build our one-way street, we're going to start with two special materials, and they're both made from silicon. You can think of them as two completely different worlds that are about to collide.
Okay, so on one side, you've got what's called P-type silicon. Now, it's been doped, which is just a fancy way of saying scientists have sprinkled in some specific impurities. This creates way more holes, and you could just think of these as empty parking spots for electrons, which act like they have a positive charge. Then, on the other side, you have N-type silicon. It's been doped with different stuff to do the exact opposite, create a ton of free-roaming negatively charged electrons. These little mobile carriers, they're the stars of our show.
So what happens the exact moment we press these two types of silicon together? Well, a totally natural process just takes over. It's called diffusion. It's the very same reason that a drop of food coloring just naturally spreads out in a glass of water. Things always want to move from where it's crowded to where it's not. So you have this huge crowd of electrons on the N side, and they see all those empty parking spots on the P side and just start rushing across the boundary. And at the exact same time, the holes from the P side are moving over to the N side. It's this massive initial flood of charges as the whole system tries to find some kind of balance.
But, this free-for-all doesn't go on forever. Actually, it very, very quickly creates its own problem, its own barrier. And this leads to a stable standoff right there at the junction.
So as those electrons rushing one way meet the holes rushing the other way, they recombine. An electron finds an empty hole, slots right in, and poof, both the free electron and the mobile hole are gone. They've just neutralized each other. And all this recombination carves out a zone right at the junction that gets completely swept clean or depleted of any mobile charges that can move around. And we call this the depletion region. It's kind of like a no man's land. There are no free electrons, no free holes, nothing's moving. And creating this empty, stable zone, that's the first huge step in building our controllable gate.
But here's the really clever bit. Something important gets left behind in that no man's land. When all those mobile carriers left, they uncovered the fixed, charged atoms that were already there. So you're left with a wall of fixed negative charges on the P side and a wall of fixed positive charges on the inside. And anytime you get a separation of charge like that, you get an electric field.
This internal electric field creates a potential difference. It's basically a voltage barrier. You can picture it like an energy hill that any new electron or hole would have to climb to get across the junction. And this natural barrier has a name, the built-in potential. Its electric field is now pushing back, stopping any more electrons or holes from crossing. It perfectly cancels out that initial rush of diffusion. So the party's over. The gate is now naturally closed. And the amazing part is, we've built the default off state for our one-way street, and we didn't even need a battery. It's a self-forming barrier.
Okay, so we've got ourselves a closed gate. The big question is, how do we open and close it whenever we want? Well, we do that by applying an external voltage. It's a technique we call biasing.
And this quote right here really nails the core idea. When we hook up a battery, the voltage we apply is either going to fight against that natural barrier, or it's going to help it out. So first up, forward bias. This is where we connect a battery in a way that pushes against that internal field. And what that does is it effectively lowers that energy hill we talked about. And once that hill gets low enough, the electrons and holes have enough juice to surge across the junction, and voila, current starts to flow. The gate is open. Now, what happens if we flip the battery around? That's called reverse bias. And now the external voltage is actually helping the built-in potential, making that energy hill even taller and the no man's land even wider. The barrier becomes so huge that almost nothing can get across. The gate is slammed shut. So here's the bottom line. Forward bias shrinks the barrier, turning the switch on. Reverse bias widens the barrier, turning the switch off. And this simple, brilliant control over an invisible barrier is exactly what makes the PN junction the perfect one-way valve for electricity. Of course, in the real world, things are never quite that perfect. There's always a catch, right? And for electronics, that catch is almost always temperature. Heat can seriously mess with this delicate balance we've created.
See, as things get harder, a bunch of things start to go wrong. The most important one is that the reverse leakage current, that's the tiny bit of current that sneaks through even when the gate is supposed to be shut, it starts to get bigger. The voltage you need to turn the thing on also changes, and even its breaking point gets worse.
So just how sensitive is that unwanted leakage current to heat?
Well, the effect is pretty dramatic. It doubles.
Yep, that's right, it doubles. And this is a huge challenge for anyone designing circuits. For every 10 degrees Celsius rise in temperature, that leaky current that you don't want, it gets twice as big. It's this exponential runaway effect. And that is exactly why your computer has a fan and why high-power electronics need those giant metal heat sinks.
Okay, so let's zoom out for a second and just look at the big picture. Why are we so obsessed with this one tiny, temperature-sensitive little component?
Because that tiny little gatekeeper, that simple one-way street we built, it is everything. A single PN junction is a diode. If you put them together in clever ways, you get a transistor, which is the fundamental switch behind all computing. And if you put millions or even billions of those transistors onto a single chip, you get the integrated circuits that run our entire world.
You know, the PN junction has been the undisputed king for more than half a century now. But as we keep trying to shrink our technology down to the size of atoms, it really makes you wonder, doesn't it? What's next? What's going to be the next brilliant innovation that acts as the gatekeeper for the technologies of tomorrow?